Reactive power plays a significant role in the efficient functioning of electrical systems, though it is often misunderstood or overlooked by many. This type of power, measured in volt-ampere reactive, VAR, does not contribute to the actual work performed but supports voltage levels in electrical systems. Reducing reactive power consumption is critical for improving energy efficiency and lowering electricity costs, particularly in industrial settings where large equipment consumes high amounts of electricity. One common solution for this issue is the installation of devices like electricity-saving boxes, which contain reactive power compensation capacitors. Reactive power and power factor, cosφ. The power factor, cosφ, is a measure of how effectively electrical power is being used. It is the ratio of active power, the power that performs useful work, to apparent power, the combination of active and reactive power. A higher power factor signifies more efficient use of electricity, while a lower power factor indicates excessive consumption of reactive power, which adds stress to the power grid without contributing to real work. Improving the cosφ factor through reactive power reduction measures not only improves energy efficiency but also reduces electricity costs for factories, enterprises, and other units utilizing the national grid. Methods for improving the natural cosφ factor. One of the primary methods for reducing reactive power is improving the natural cosφ factor. This approach involves optimizing the operational efficiency of electrical equipment so that less reactive power is needed from the power source. The following measures are common for enhancing the natural cosφ factor. Technological process optimization. Electrical equipment must operate in the most efficient mode. This may involve adjusting processes or redesigning systems to better utilize electrical power and reduce the reactive load. Motor replacement. Underloaded motors can waste significant energy. Replacing these with motors of appropriate capacities can drastically reduce reactive power consumption. Idling motor limitation. Motors running without load can consume unnecessary reactive power. Limiting the number of idling motors can help optimize energy usage. Synchronous motors. In certain situations, switching from asynchronous to synchronous motors can provide greater efficiency and lower reactive power requirements, as synchronous motors offer better control over power factor correction. Transformer optimization. Underloaded transformers can be replaced with smaller ones to minimize reactive power loss. Properly sized transformers result in more efficient energy distribution and less reactive power demand. Methods for artificially increasing the cosφ factor. When improving the natural cosφ factor does not fully address the issue, artificial methods are employed, mainly through the installation of reactive power compensation devices. These devices supply reactive power directly to the electricity consumers, reducing the amount of reactive power that needs to be transmitted from the power grid. There are two primary methods for achieving this. Synchronous compensators. These devices operate by using a synchronous motor in no-load mode. They can both generate and absorb reactive power from the grid. Advantages. Synchronous compensators offer dual functionality by either producing or consuming reactive power, making them highly versatile. Disadvantages. They are complex systems with rotating parts, which require careful assembly, regular maintenance, and sophisticated operation. Therefore, they are typically used for centralized compensation with large capacity needs. Capacitors. Capacitors are a simple and widely used solution for reactive power compensation. By causing the current to lead the voltage, capacitors generate reactive power to supply the grid. Advantages. Capacitors are easy to maintain, have no rotating parts, and are cost-effective, especially for small and medium loads. They can also be adjusted according to the evolving power requirements of the load. Disadvantages. Capacitors are sensitive to voltage fluctuations, making them less reliable under unstable conditions. They have a limited lifespan and are prone to damage from short circuits or excessive voltage. Additionally, residual voltage can remain after disconnection, posing a risk to operators. Electronic circuit technology and overunity claims. Electronic circuits, such as those found in electricity-saving boxes, are often marketed as devices that reduce reactive power consumption. These circuits can generate secondary power sources by converting electrical signals, e.g., pulses and noise, from the grid into usable power. In theory, this allows the device to recycle energy that would otherwise be lost as noise, contributing to energy savings.